All right, welcome back, everyone. So in this next session, it's going to be mostly focused more on adaptive experimental design, but also moving more into hybrid models, where instead of IID observations, maybe what observations you have are reflective of agents' different behavior. And also, if we have different an experimental design setup where you're making treatments and getting observations, but maybe now there's bleed over between the treatments, and how do you deal with that? And so our first up speaker is Kyra again. She got a PhD in operations research at CMU, and she's starting as an assistant professor at ORIE at Cornell Tech. And she's an expert in adaptive experimental design, causal inferences, and also has a particular focus on medical applications. And today, she's going to talk to us about her work on adaptive hypothesis testing.
Sure. Thank you so much for the introduction. I just want to mention briefly that I'm joining Cornell Tech next fall, and I'm currently doing a postdoc at Harvard with Susan Murphy. So let's get started with this greedy approximation algorithms for the problem active sequential hypothesis testing. And let's first start with the fun part, the motivating example. So here we are actually going to be talking about cancer research or treating cancer. So we have known for a very long time that the success of cancer treatment is highly associated with the stage that cancer is detected. So nowadays, even with very comprehensive screening policies, the percentage of cancer that's actually being detected in early stage is quite low. So here I'm taking some statistics from the Canary Foundation. So ovary cancer is one cancer type that has established screening policy, but even though only 15% of those cancer cases are caught in early stages. And now if you look at the 5-year survival rate for if you catch this in early stage versus not early stage, the survival rate drops significantly. So there has been something circulating in the medical community for a hope called the liquid biopsy. So we all know what a regular biopsy is, right? The regular biopsy, simply you have a procedure, dig a tissue out of your body and perform lab tests to see whether you have cancer or not. And what a liquid biopsy is I want to kind of still be able to detect cancer with high accuracy, but this procedure should be minimally invasive. And the whole idea is to perform this procedure using a blood test. So now let me just move on to how this could actually work in practice, right? Why we hope that liquid biopsy blood tests can be actually used to detect cancer. So this actually based on a few facts. The first fact is that cancer is caused by mutations, and our tumor will contain mutated DNA. And the second fact is that when a cell dies, it actually sometimes releases its DNA into the bloodstream. So if you have tumor, then your blood will have tiny traces amount of mutated DNA, and that should serve as a signal for whether you have cancer or not, right? And the DNA that's circulating in your blood, we just call it the cell-free DNA. Now, if we have all the money in the world, this problem is kind of solved, right? We can just sequence all your genetic addresses to see whether it contains mutated DNA, then that I should know whether you have cancer or not. But the challenge here is really the cost, because a human being has 3 billion different genetic addresses, right? So it just turns out those cell-free DNA has very, very low concentration in your blood. And let me be more precise, it's 10 to the -4. So if you want to avoid a false negative result, you should probably sequence one particular genetic address for 10 to the 4 times. And the cost for that is roughly around 1 cent. So now let me just add more constraints to say that a reasonable commercial test should cost no more than $100. So this really forces us to pre-select around 10 to the 4 number of genetic addresses in a liquid biopsy panel. Right? What we are going to do next is to kind of reframe this problem in the language of active sequential hypothesis testing. And what I'm going to show you next is just an ASHT instance. And for now, I'm just going to claim that the problem I just described in words can be packed into this table with one additional parameter. And let's just work on the problem setup now. In the problem of active sequential hypothesis testing, we are given a set of hypotheses, right? In the cancer example, these are just different types of cancers that I'm considering that the patient might have. That corresponds to the rows of this table. So in this particular example, I'm considering 8 different cancer types. So this table contains 8 different rows. So now among one of those hypotheses is the unknown true hypothesis H star that I want to identify. All right, meaning that one of those particular rows corresponds to the cancer that a particular patient has. Moreover, we are going to assume that we know the prior pi according to which the true hypothesis H star is drawn. In the cancer example, this just corresponds to that the clinician has a very good understanding of the probability this particular patient to have different cancer types could be based on their family history, their gender, age, and things like that. Now, in the ASHT problem, we are also given a set of actions that we could perform, right? Going back to the genetic example, that just corresponds to different genetic addresses that I could potentially sequence. And the action in this table corresponds to a column, right? So we have 3 billion genetic addresses. So we have 3 billion columns inside this table. Now, once I perform an action, I'm going to observe an outcome that's generated according to the true hypothesis. And here the outcome is 0 or 1, but it's not deterministic. So I'm with certain probability, I'm going to see a mutation, that's 1. And with certain probability, I'm going to see no mutation 0. So now what are the entries of this table, right? If you think about this binary outcome distribution, it's simply a Bernoulli random variable with a mean. And the mean is specified by the entry of this table. So under the ASHT problem, in addition to the set of hypotheses and the set of actions that we are given, we also know the outcome distributions for each action and hypothesis pair. So that is given. In the liquid biopsy example, this is sort of to say that using past knowledge, past data, and domain knowledge, I kind of know for a certain group of patients, what's the probability of observing a mutation under certain cancer types. So let me just be more precise with the binary Bernoulli distribution here. Let me just assume that the third row here is my true hypothesis, right? The patient has this particular type of cancer. Then I perform the action that corresponds to the first column here. Then the outcome that I'm going to observe is going to be 1 with probability 0.01. Now, right, just to recap the ASHT instance, you can just think of it as the prior pi plus this table that we are seeing here. Now, before I move on, I want to highlight that the outcome distribution can actually be more than Bernoulli distribution in our work. It can also be applied to Gaussian distributions, but for the simplicity of this talk, I'm just going to be focusing on this Bernoulli case throughout. So now having stated the input to the ASHT problem, right? What is the objective? I know the set of hypotheses, I'm given the set of actions, right? I also know the outcome distributions that I will observe once you perform an action. The goal is to kind of, again, identify the unknown true hypothesis H star with high probability at minimum expected cost. All right, again, without the cost constraint, this problem is trivial. So to denote, just to formally denote this probability of identifying the true hypothesis, I need one more parameter, delta, to denote, again, the probability of identifying the wrong hypothesis. and formally stated, right, the goal of an ASHT problem is to identify the unknown to hypothesis H star with high probability at minimum expected cost. Now, if you abstract away and think about in terms of the liquid biopsy example, this is to say that we want to identify, doesn't matter what cancer type that this patient has, when my algorithm terminates, I kind of want to identify this correct cancer type with high probability, right? So there's kind of some fairness inside this objective. You want to be fair to unknown hypothesis H star. So it turns out that this problem is NP hard and we don't have an exact solution for this. So we will be focusing on discussing two approximation algorithms in this talk. And we will consider two types of adaptive algorithms. All right. So the first type of adaptive algorithm is partially adaptive, meaning that I'm going to first fix my action sequence according to some objective, greedy objective. Then I'm going to play the actions in my action sequence one by one. And once the algorithm's exiting criterion has met, then I'm going to terminate. So really the key part is how do you construct this action sequence beforehand without knowing which one is the true hypothesis. And to provide theoretical guarantees under this partially adaptive algorithm, we're going to be using a tool called submodular function ranking from kind of discrete optimization world. And one of the objective of this talk is to simply introduce you what this tool is. And the second type of adaptive algorithm that we consider is the fully adaptive algorithm. So at this time, you can perform actions one by one. You are going to see the outcome from your previously performed actions. Then based on that information, you are going to select the action to perform in the next step. And also you're going to adaptively terminate the algorithm. And to provide theoretical guarantees, we will be using tools from optimal decision trees. Now, before I move on to introduce you the two algorithms in our work, first, I want to show you a summary of the results. So we will first look at our partially adaptive algorithm and compare against two benchmarks. One is just brute force, right? I can just search through all the action sequence and find the best permutation in a partially adaptive case. And then we will compare it also against two LP heuristic that's from past literature. So this is kind of an algorithm that you are constructing one randomized policy to play according to at each iteration. And then we will look at two performance metrics. One is runtime. The other one is approximation ratio. And just for a reminder, approximation ratio is the ratio between the objective of an algorithm to that of the optimum algorithm. So here I will not define what an optimal algorithm is, but I will formally state it later on. So here just to give you a sense of how those three algorithms compares. So for brute force, you do, because you're searching through all the action sequence, you get this A factorial runtime. For the LP heuristic, again, we're just coming up with one randomized policy to perform according to at each time step. This really corresponds to solving one linear program with size A times H squared. And to the best of our knowledge, this LP heuristic algorithm doesn't have any approximation guarantees. And now for our algorithm, the runtime, right, to construct this action sequence, it is linear in the number of action and number of hypotheses per iteration, but our algorithm also admits approximation guarantee of log H. Now to see the fully adaptive case, again, we are going to compare our fully adaptive algorithm with brute force and this algorithm proposed by Nashvar and Javidi in 2013. This is a two-stage algorithm that used the first LP heuristic as a stage one policy. And then once the posterior probability of a hypothesis exceeds certain threshold, I'm going to move into stage two. So for stage 2, I'm going to solve a different linear program each iteration, right? To coming up with a randomized policy that favors that particular hypothesis exceeding my threshold. So that's the runtime is solving LP per iteration with size linear in the number of action times number of hypotheses. Now our algorithm has a similar runtime per iteration, but we have approximation guarantee of log square h. So this is just a summary of our results. Any questions so far?
Do you elaborate on the cost here? So the cost is the number of addresses that you check, like
Yes.
the number of samples?
Yeah, here we're just considering uniform costs. So sequencing each genetic address will be cost the same. So the cost is just the number of addresses that you perform.
The probabilistic guarantee is a constraint. I need to reach this 1 minus delta.
Yes, outperform. Yes, exactly. Yes.
Regarding the per iteration cost, how many iterations does the algorithm need?
So for this, you can kind of thinking I'm going to construct an action sequence, right? But I don't need 3 billion. I don't need the full permutation of the entire action sequence. I can truncate maybe at 300, 500, things like that. And we're looking at the order like around hundreds and thousands for iterations. So like usually in our experiments with the cancer example, our algorithm usually terminates before performing like 800 actions.
Is there a theoretical upper bound on the number of iterations?
Well, yeah, that will correspond to the sample complexity that you will need to terminate. Yeah, that you will need, but we didn't analyze that in the paper. I think this paper they had something that's similar to the samples that you need to terminate. But this is not.
But it will depend on the gap, right? So if there are two hypotheses which are very close, it can take forever. So
Yeah,
it will be a
so
gap
it's like, yeah, it depends on like the stopping point for the optimal algorithm and like, but in terms of that, like, it's an extra log h cost. First, I guess.
Just to check that I understood properly. So compared to like typical banded stuff, you require that the algorithm is able to verify that it has found the correct hypothesis, right? So this is harder because you ask the algorithm to also tell you that I'm sure I have found it.
You need to be able to. It's identification versus kind of yeah.
If you want to compare to bandits, I think the main difference is that if you send the same address twice, you get the same outcome here. Whereas in bandits, you will get different outcomes normally, right?
Yes, so here you actually don't. So when you perform an action, you actually see binary outcomes with certain probabilities.
Yes, and so if I perform the same action 2 times,
Now,
I get 2 different outcomes for the same outcome.
2 different outcomes.
Here as well.
Here as well.
Because I see that like in biology, it would make more, okay, I see that it's a new measurement, new noise somehow. Okay.
Yeah, so the idea behind the biology is that even you sequence the same genetic address twice, it's not guaranteed that you're going to see a mutation because some sequence contains
It
mutation.
depends on how we think about the noise.
Yeah, but yeah.
I see. Okay, but it's so scary.
So again, in that table, you showed us these numbers can like change if I tap the same table entry twice.
So the entry will not change because that's the mean of the Bernoulli distribution, but the outcome could change. You could either see for one.
Okay, so it's just a mean. Okay.
Yeah, that's just the mean.
Okay, so it's not a table of
Yeah.
numbers, it's a table of
It's almost like best. It's hypothesis identification. I'm like, whatever. Right? Like, yeah.
Yeah.
It's positive. Yeah. It's good.
Sorry, I thought I understood the model, but now I'm confused now. So if you can probe the same column more than once, why is the optimal solution a permutation? Like you should, like the optimal solution might involve probing the same column.
So you don't know which cancer type.
But if you go
So
forward
depends on-
that slide,
yeah.
like the why is the brute force?
Yeah, for the brute force.
Yeah, why is the brute force like a factorial or something? Sorry, like to the results.
It's worse than a factorial. The
To the
optimal
results table, I thought if you go to the results table, I thought the runtime of the brute force is like. Oh, okay, but
But then
there's.
you need to try like which one is the best one because you don't know which hypothesis you want to identify at this time. Right? If I don't know which hypothesis. If I know my hypothesis particular row, that I know which one's the optimal. Okay, so I think I think maybe you already practiced brute force probably will terminate earlier than a factorial number of actions, right? Yeah.
Do you need to assume anything about the gap?
Yes. Okay, that's something I'm hiding. So we do require a parameter on the minimum separability of the entries in the table. So like we require like the Cal divergence between those two distributions is separated by a parameter called S. And that's a parameter in which like our theoretical guarantee will depend on. Right? You should expect the smaller the gap is, the worse the approximation guarantee is, right? But for simplicity, I'm just hiding that parameter here. The dependence is proportional to 1 over S. Yep. Any other questions? So what I'm going to do next is really to show you how the partially adaptive algorithm will work. And the way that we'll do that is first to give you some intuition of how we would proceed even to think about this problem in partially adaptive case. And the way that we're going to do that is by reducing this stochastic outcome to deterministic outcome. That's first to say that if I perform the action and it gives me binary outcomes, then how when an algorithm will say that I have identified the correct hypothesis. So here we have the table like we had before, right? Each row corresponds to a hypothesis and each column corresponds to an action. However, now if I perform an action, right, under any hypothesis, I'm going to deterministically see either zeros or ones, right? And let me simplify this problem further for you to say that I know that row 1 is my true hypothesis, right? My goal is to identify this hypothesis by performing actions. Let's just walk through one of such exercise, right? Let me just going to pick this arm 1 that corresponds to the first column. And when I perform this action A1, because I know that my true hypothesis is H1, so the outcome that I will observe will correspond to the entry 0 here. Now, if I look at the entries of the rest tables that corresponds to A1, the only inconsistency that I will see in the potential outcome will be the one that corresponds to my hypothesis 6. So by performing this action A1, now I can say that I have ruled out hypothesis 6 to be my true hypothesis. So I'm going to keep performing more and more actions until there's only 1 left. And then at that time, I'm going to say that I have identified the correct hypothesis. All right, so this is not to say that I'm showing you an optimal action sequence in any sense, but to see how ruling out a hypothesis would work in a deterministic case. Now, going back to our stochastic instance, let's just think how we would approach this, right? How would we rule out one hypothesis? So let's just go over the same exercise. Let's say, suppose row 1 is my true hypothesis. One very natural idea is to say I'm going to rule out another hypothesis if the log likelihood ratio between those two hypotheses exceeds certain thresholds, right? So what is the log likelihood ratio? I just need one more parameter to denote the outcome that I observe at time I, when action AI is performed, then the log likelihood ratio between H1 and H2 will simply look like the following, right? In the numerator here, we have the probability of observing OI under my hypothesis 1 and A1 as my kind of data generating process. And in the denominator, we're simply replacing H1 with H2. And we're summing over all the actions that we have performed so far here. So now this expression actually has a problem. What is that? Right. So the problem is actually this OI that I observe at each time I is random, right? So this quantity, depending on the path, would actually be different for different realization. So this causes a problem because we're saying we're ruling out a hypothesis according to some random quantity, and we do not want that. So the solution that we come up with is simply to take the expectation of this quantity when we are performing the ruling out step. So it turns out that the expected log likelihood ratio is a very nice looking form, right? It simply is the sum of the KL divergences specified by my the Bernoulli distribution specified by H1 and AI, and the Bernoulli distribution is specified by H2 and AI. So kind of the idea here is really you are collecting more and more KL divergences by performing more actions, right? To kind of give you the confidence of how those two hypotheses, how to rule out one hypothesis. So let me just make this idea more concrete when I move into the partially adaptive algorithm. You will see we will use that idea that we just talked about as a subroutine. So for our partially adaptive algorithm, let me just give you the outline of the algorithm again. So the input is going to be an ASHT instance. Again, it's the prior pi and the table that we've seen in the previous slides. And we also are given the error tolerance delta. All right, so what I want is when an algorithm terminates, I want my algorithm to be able to identify the correct hypothesis with probability 1 minus delta. I will construct the action sequence according to the greedy objective that I will describe later. Then here we are going to boost each action in my set for sufficient many times to obtain sigma tilde. This is because we want to because of the stochastic nature of our instance, we want to perform an action sufficiently many times to be able to say the difference between two hypotheses. And now what we are going to do next is by performing the action in the superset 1 by 1 and terminate there's only one hypothesis left. So to create the greedy objective for constructing the action sequence, we will be using this tool called submodular function ranking. Again, this will use the intuition that I talked about as a subroutine. So here we will so the goal for submodular function ranking is to identify or cover a hypothesis. So at each time step, right, we will consider a true hypothesis H. And then I'm going to use this capital letter S to denote the set of actions that we have performed so far. And I have a threshold for when to say that I've collected enough KL divergence to rule out a hypothesis. So the first thing that we need to keep track of is the progress that we have made so far towards ruling out a particular hypothesis G under H. All right, the way that we are going to do that is by using the following function, capital K, subscript by H and G. Inside the minimization term, we have our threshold B. And in the summation here, we're simply calculating the KL divergence that we have collected so far in my action set S. Right? So if I've performed enough action, I'm going to hit my threshold B, and this function will take the value 1. So a sanity check. right? This function takes the value 1 if I have ruled out hypothesis G under H, and the minimum value for this function is 0. Now, the second thing that we need to keep track of, right, to identify H, I need to rule out all the other hypotheses in my set. I kind of also need to keep track of the progress that I've made towards identifying H. So the way that we will do that is by using this function f subscript by H. All right, in the summation here, we're simply summing over the progress that we are making towards ruling out each individual hypothesis in my set that's not H, right? So this function will take the value 1 if and only if I have ruled out all the other hypotheses in my set, and this is to say that H is identified. So for those of you who cares, this function is actually submodular. And now we can talk about the greedy algorithm that we use to construct the action sequence. So far for submodular function ranking, we have a function that keep track towards of ruling out all the other hypotheses in my set. So here, overall, how we're going to construct the sequence if I do not know the underlying true hypothesis H, right? So at each step, we keep track of this set of actions that we have performed so far using this capital letter S. And then at each step, I'm going to choose the action has the following highest score. Now in the numerator here, this is simply the incremental coverage with one additional action. And in the denominator here, we're just favoring the hypothesis that is about to be covered. We are weighting this fraction using the prior for each hypothesis. And here we are summing over all uncovered hypotheses. So that's our greedy objective. So using this greedy objective, we will be able to calculate the action sequence and do what we just said before in the algorithm outline. And here I want to just say that, so when do we determine that my algorithm will stop, right? I have my action sequence. I perform the actions one by one. Then my algorithm will terminate when the log likelihood ratio between one hypothesis and the remaining hypothesis is above a certain threshold. So this actually depends on the realization of the instance. So now just to state the theoretical guarantee for the partially adaptive algorithm formally, I'm going to introduce a notion of delta error algorithm. So I'm going to be called an algorithm that satisfies this delta error property if it identifies any true hypothesis with probability 1 minus delta. Now, for our partially adaptive algorithm, we can show that our proposed partially adaptive algorithm achieves this delta error with expected cost at most the following amount times the optimum. So what's the optimum? The optimum is the minimum cost algorithm among all partially adaptive algorithms that achieves delta error. Now to parse this term here, I'm going to be looking at the special case where delta equals to h to the minus c. If you plug in this value to your expression, you actually get the following approximation ratio. And I want to highlight that the first term is the approximation ratio lower bound for the ASHT problem. So this is really to show that our approximation guarantee is tight with respect to this parameter h. So now I'm going to quickly run through the fully adaptive algorithm. So now the challenge is to kind of incorporate the observations that you have made so far towards selecting the next action. And the way that we will incorporate that part of the information is by creating this idea of alive sets. So the set of alive hypotheses are the ones that are consistent with my previously observed outcomes. So to remove the noise, right, from the problem instance, we're going to repeat each action sufficiently many of times, right? That's how we reduce to the optimal decision tree problem. And then we're going to greedily choose the meta action that rules out the most alive hypothesis in the worst case. So once we perform the action, we're going to see outcomes, and we're going to take the empirical mean of the outcome, right? At this time step, I'm going to say I will rule out those hypotheses that's inconsistent with the empirical outcome that I observed. All right, so again, we will terminate this algorithm when there's only one hypothesis that's left in my set. So quickly running through the theoretical guarantees, we have just the same setup as we had in the partially adaptive case, just the approximation ratio is slightly different. We will do the same exercise by substituting delta equals to h to the minus c. And that's how you get the log square h term here in the approximation factor. Moving on to experiments. I guess I have like 7 minutes. Okay. So let's skip the synthetic part. So Cosmic is the public data set for genetic mutations. So you will, in this data set, you will observe the genetic mutation for each cancer patients, curated over the past history. Now, what we are doing in this table here is we are looking at 8 different cancer types. So that's 8 different hypotheses. And we're looking at genetic address intervals as our action space. So the x-axis here are the accuracy of the algorithms. So we're looking at 4 different algorithms in this figure. And the y-axis is the average number of samples that are used when the algorithm terminates. So we're comparing the LP heuristic, that's the benchmark for the partially adaptive algorithm, against our partially adaptive algorithm, that's NJ adaptive. So that's the first solid line there. And we are comparing partially adaptive algorithm. Wait, sorry. So we are comparing the performance. Sorry, I got that wrong. So we are comparing the performance of the LP heuristic with our partially adaptive algorithm. That's the second dashed line there. And then we are comparing the algorithm proposed by Nashvar and Javidi for their two-stage algorithm here that corresponds to the first solid line, and the performance of our algorithm, that's the bottom solid line here. Kind of the overall message here is our proposed algorithm does outperform the existing benchmarks. I guess the key question that you're asked is probably what's the sensitivity and specificity, and those are kind of important in the medical test. And here are the results. If you think about the objective of ASHT problem, it is kind of saying that condition on that this patient has a particular cancer, right? When my algorithm terminates, I want to have delta probability of identifying the wrong hypothesis. It's kind of the sensitivity of a cancer type test. So here we do see that our algorithm achieves quite high sensitivity and specificity in general, compared to the existing liquid biopsy test, which I'm not showing here. But that concludes the entire talk. Thank you so much for your attention.
We have time for a few questions.
So can I treat the theorems as bounds on stopping time? Like the cost, is it the number of?
It's not the cost. So we're comparing the performance of our algorithm to that of the cost. So we're not really characterizing the optimal policy. We're not saying when the optimal policy determines how many samples are needed. But to compare the performance of our proposed policy with that of the optimal policy.
So this is why it will depend on number of actors. Or like you were just mentioning.
Yeah, so no, so the approximation guarantee is independent of the actions. So that's the key part, right? When the action space is very large, this result's kind of nice because your approximation guarantee is independent of the number of actions.
So I like this seeing that function with some of the KLs as a submodular function. Could you have solved for, like, could you have made it a continuous problem? Then each, so it's like you're trying to solve for a probability distribution over the actions, and then use some rounding technique to do it. Do you guys think of that as just like, I was just curious.
Can you just be more specific about rounding?
Yeah.
I think the LP does that.
Yeah. Okay, so that the LP solution, that's she was solving for the continuous one. Okay.
So have you done any cost of adaptivity analysis? Like, for example, how does the partially adaptive solution compare to the fully adaptive?
So we do have the performance here.
Yeah, but you're comparing the partially adaptive solution to a partially adaptive pop. Can you compare the partially adaptive solution to a fully adaptive?
In terms of number of samples?
Yeah.
So here's experience. Like we don't have theoretical results for that because we are not considering sample complexity as a metric, right? We're comparing just to ops of the performance of our algorithm against ops. But like for the numerical experiments, right? Those are at the same accuracy, right? If you reach the same accuracy, you will see that fully adaptive algorithm requires a lot less samples than the partially adaptive algorithm, and that's matches our intuition, right? That should be the case in practice. So yeah. I hope that answers your question.
What was the definition of partially adaptive?
Right. So for partially adaptive algorithm, you will construct the action sequence a priori. So once you run the greedy algorithm to construct the action sequence, that action sequence is fixed.
Okay.
Then you perform the actions one by one, and then you will adaptively choose when to stop. You don't have to run through all the action sequence to terminate.
Okay, so it's basically fix an action sequence, and then as you go, stop early if you want.
That's right.
Okay. Thank you. Very good.